Okay, thank you very much. Before I begin, I'd like to acknowledge a number of collaborators whose work is manifest in this presentation. Those including Dr. Mohamed Atune, formerly Thornton Tomasetti, Professor Kensho LoRa at Stanford, Elizabeth Moji, colleague of mine at University of Michigan in the School of Education, and Peter Jansen, who's the bridge engineer for Michigan Department of Transportation. The title of the presentation is Enhancing Urban Resiliency Through Smart City Technologies, Prototyping Solutions with Cities. So because the talk will be primarily focused on resiliency, let me begin by talking a little bit about some of the stressors that introduce resiliency as a foremost topic within the profession of civil engineering. So many times as civil engineers, we're often concerned about natural hazards that often present tremendous loading on our infrastructure that can lead to damage and destruction. For example, we've seen a number of very large-scale earthquakes across the globe leading to massive destruction. Shown here is an example of the Tohoku earthquake in 2011, a 9.0 earthquake that led to a number of cascading failures. Earthquake followed by tsunami breaching seawalls, leading to damage to a critical nuclear power facility that left some nuclear material to radiate from that particular facility. This destructive earthquake led to over $200 billion worth of damage to the Japanese economy, underscoring the need to be resilient against these type of hazards. Another example of hazards are tropical storms. This is actually the largest, most natural hazard that we see posed to our habitat across the globe, especially in the United States. And shown here is an example from last hurricane season, 2018, Hurricane Michael, which was a Category 5 hurricane that struck the northern coast of Florida, leading to massive destruction, really underscoring the need to be resilient against these type of hazards. In the case of natural hazards like hurricanes, we're seeing an increasing number of hurricanes as well as increasing intensity posing threat to our habitat. If we look at just last year's hurricane season, we saw 15 named storms, 8 large storms, and 2 very large storms with destructive power like Hurricane Michael. Other examples that introduce questions around resiliency for our habitat are things like climate change. Climate change is occurring, whether it's human-induced or not. It is definitely occurring and is projected to have increased global warming of upwards of 10 Fahrenheit degrees by the end of next century. We're also seeing increasing rising sea levels projected to increase 1 to 4 feet by the end of the century. And we're seeing dramatic shift in the availability of water across the globe. In the case of the United States, we're seeing a dramatic change in where our fertile land is compared to our arid land, and that has very profound effects on our agriculture and the availability of water that we need for things like drinking water. For example, if we go back in history in 1878, American geologist John Wesley Powell demarcated the 100th meridian, which is the separating mark between essentially our dry arid regions in the western part of the United States and our very moist fertile regions in the eastern United States. But due to climate change since that time, that meridian's actually moved over about 400 miles. And today the demarcation in the United States is the 98th meridian, meaning that 400 miles across from north to south in the United States has had dramatic change in the availability of water, which has profound impact on our agricultural industries in the United States. And again, that introduces resiliency of our infrastructure, our food supply, as well as our water availability. Other types of concerns associated with resiliency is our rapid urbanization across the globe. We're seeing, for example, a massive wave of urbanization that's led to now more than 50% of the world's population living in very large cities. And we have a large number of megacities of 10 million or more residents within a very confined area, increasing essentially the stakes when hazards occur because of the complexity of addressing natural hazards and man-made hazards in such dense urban areas. Another challenge associated with urbanization is the resiliency of our infrastructure. In many mature economies, we're able to plan ahead and plan accordingly to be resilient against stressors. But in many emerging economies, we see that there's waves of chaotic growth that introduce a lot of vulnerabilities in their infrastructure and the ability to withstand stressors. Another challenge that introduces vulnerability in our infrastructure is aging infrastructure. For example, in the United States, most of our infrastructure was developed after World War II and is now approaching the end of their intended design lives. And when we have essentially aging infrastructure, we have deterioration that can introduce weaknesses in those infrastructure. An example shown here is the San Bruno pipeline gas failure, which occurred in 2010 in the San Francisco Bay Area. It was essentially undetected corrosion of a pressurized gas pipeline, leading essentially to an explosion of that pipeline, destroying essentially a neighborhood in the San Francisco Bay Area, leading to 8 fatalities. And that essentially introduces the risks that are essentially evident when we don't address our aging infrastructure. Other stressors can also be economic downturns. This is a big issue in the United States, particularly in the part of the United States that I come from, the Midwest, where we've seen essentially a very dramatic change in our economic makeup of our local economies. In the case of the Midwest, we've shifted from essentially a manufacturing-based economy to one that is not. And that unfortunately has left a lot of people without available employment opportunities, leading to things like shrinking cities. And shown here is a picture of Detroit, which is one of the largest shrinking cities in the United States, where we've seen dramatic population declines of upwards of 60% of its population being lost over a 60-year period up to present day. Now, when we think about resiliency, we can look at the definition of resiliency. So for example, if I look at the dictionary, the definition of resiliency is the capacity to recover quickly from difficulties, toughness, essentially. Now, from an engineering perspective, we often like to use functionality resilience curves to define and quantify our resiliency of our infrastructure. That particular performance curve typically is a time-based performance curve that's looking at performance before and after a disruptor event. So before the event, we may have normal performance. We have a disruptive event that can essentially erode some performance metric that defines how our infrastructure is performing. Essentially, over time, we can start to build back the capability of that infrastructure, essentially leading to a recovery effort. And that recovery effort can be delineated both short-term as well as long-term until we achieve full performance back after that particular event. Now, from an engineering perspective, we often like to look at the area that's underneath the curve off of essentially the normal performance level of 1. And we typically will integrate essentially that performance index or that performance curve -1 over the time period from the disruptor event to full recovery. And that scalar is the way that we typically or historically would define resiliency. But this particular approach to defining resiliency is potentially an oversimplification of a lot of competing and a lot of different dimensionalities that go into resiliency. A broader definition of resiliency has been introduced by the National Infrastructure Advisory Council, which is an advisory council to the President of the United States, and is essentially congregated by the Department of Homeland Security. And they define resilience along what they call 4 properties of resilience, and that includes robustness, rapidity, redundancy, and resourcefulness. These 4 properties of resilience can be mapped onto 4 dimensions associated with resilience, ranging from technical, organizational, social, and economic. And they also explore the results of resilience. Once we think about resilience among these 4 R's and in these 4 dimensions, what are the results? And that can be more reliability of our systems, whether they're physical systems or human systems, lower consequences of stressor events, and faster recovery time periods, which is really the long-term aim of being resilient, is to be able to recover more quickly. Now, if we think about the 4 dimensions of resilience, technical, organizational, social, and economic, as well as the 4 properties of resilience, which is a way that we can begin to objectify measures of resiliency, we see tremendous opportunity for smart city technologies that can come in and provide essentially the data and the information that's necessary to drive these type of analyses. So by broadening the definition of resilience and looking at different dimensions and different properties of resiliency, we can more richly define what resilience is for our society and think about community resiliency along these dimensions and the appropriate approaches to sensing and actuating our infrastructure and our societal systems to be more resilient along these properties and dimensions. Now, fortunately, there's a number of emerging technological trends that holds great promise for introducing the technologies necessary to make our society more resilient. Thinking about technologies that may layer upon many of our infrastructure and social systems that allow us to be more resilient. For example, we've seen an explosion in computing power since the 1960s that's best encapsulated by Moore's Law, where we essentially see a doubling of computational power every 18 months. A trend that's held unmitigated up until recent times, but we've been able to push ahead through technologies like parallelization and parallel architectures in our computing domain. Another technology that's emerged is essentially wireless telemetry or wireless communication. And we're seeing increasing availability of communication bandwidth that allows us to communicate data through wireless means. And this simplifies the communication of data as well as lowers the cost and essentially the scalability of communication between devices and between people. We also have seen from the 1960s to the modern day essentially a revolution in sensing technologies that's really been born out of technologies like MEMS, micro-electromechanical systems, where we've been able to use integrated circuit technologies to build sensors. And the benefit of using integrated circuit technologies is that we can build sensors in batch fabrication methods, thereby driving their costs down, but also driving their size down to miniaturized levels. And shown here is a MEMS-based accelerometer, which is a mainstay sensor technology today within the infrastructure space. We've also seen, due to the emergence of technologies like CCD, essentially the ability to have a proliferation of cameras in our society. This is actually one of the most widely distributed sensors that we have within the built environment, our cameras. For example, here in the United Kingdom, it's one of the largest distributed closed-circuit television networks in the world, with nearly 500,000 cameras in the London metropolitan area. In cities like New York City in the United States, we have over 15,000 CCTV cameras that are distributed throughout the city, providing true big data, massive amounts of data that's very rich in both its context as well as in its availability over time. The last technology that's converged, that's really changed the availability of sensing and actuation solutions for infrastructure is the internet, which is one of the greatest technological achievements of the 20th century because it's really opened unprecedented connectivity across the globe between people, between machines, as well as between essentially information brokers and information consumers. Now, if we converge many of those technologies, we've seen the ability to apply those technologies to drive resiliency in our infrastructure. So one of the first examples of adopting sensing and actuation technologies to make our infrastructure more resilient is the introduction of monitoring systems as well as control systems. And there's many examples of that coming out from the mid-1980s all the way to the modern day. For example, in California, we have a strong ground motion instrumentation program that's led to the deployment of dense arrays of accelerometers within many of our marquee critical structures like the long-span bridges. And shown here is the Golden Gate Bridge, which has over 100 accelerometers installed within it for permanent seismic monitoring applications. We can also embed actuators in our infrastructure to essentially allow infrastructure to react to stressors like earthquakes. An example would be the Mori Tower in Tokyo. This impressive structure in Roppongi has over 350 semi-hydraulic actuators. There are semi-active devices that are intended to limit deflections of that structure during typhoon winds, as well as small to moderate earthquakes. Many of these different systems, whether it's a monitoring system or a control system, have largely been driven using physics-based approaches to our analysis, both in how we're interpreting the data collected, as well as the control laws that are being applied. So these are largely partial differential equation approaches to essentially using our data and using it to both understand performance as well as control. Now, more recently, because of the availability of the internet, we've seen a dramatic shift in our approaches to monitoring and control. And that can be best encapsulated through the emergence of what are called cyber-physical systems. So cyber-physical systems are distinctly different than structural monitoring and structural control systems because of the internet and the availability of computing power that gives us scalable, on-demand computing capabilities that essentially is driving the adoption of new types of approaches to interpreting our data. Going, for example, beyond differential equation-based physical methods, to ones that are more data-driven, based on concepts like machine learning, among other types of approaches that give us the ability to essentially process large tracts of data. And then using the interpretation of that data from our cloud-based analytics to essentially drive our control solutions. Whether it's in the reconfiguration of the control system or a completely new control law that may be dropped in based on the computing capabilities that we see in the cloud. Many examples exist of these cyber-physical systems, including earthquake early warning systems that are able to take ground motion parameters, essentially process that fundamentally in the cloud, and then use that to actuate critical systems like bullet trains. And we see a very mature and extensive network deployed in Japan, and the beginning of a deployed system in the United States as well. Intelligent transportation systems is another example where we see connectivity in cars. Connectivity giving us enhanced safety because we have full situational awareness as we drive our cars within our roads. We can go one step further beyond connectivity and introduce autonomy. Again, fundamentally a cyber-physical system approach to essentially processing our data and then actuating these autonomous vehicles for safety applications. Another example are smart grids, a necessary technology that allows our grids to accommodate renewable technologies, for example. Also, cyber-physical systems are at the root of essentially driving resiliency within our smart grids, being able to be more reactive to changes in supply as well as in energy demand across our grid. Now, even beyond cyber-physical systems, which is a technology that's currently under development today, we're now seeing what I would consider to be the ultimate cyber-physical system, and that being the smart city. And there's many examples of different smart city architectures that have been proposed globally. But one of the ones that I personally like is the one that Sidewalk Labs has developed and is now implementing in the Quayside development project in downtown Toronto. And the reason I like their particular approach to viewing smart cities is due to their interpretation of smart city services being layered on different types of functional layers. Now, the layers that we're perhaps most familiar with as civil engineers is the physical layer. That can be our critical infrastructure systems like our water delivery systems, our energy systems. But also our physical systems includes things like buildings and the built infrastructure we depend upon for our habitat. Now, we can introduce essentially data and information through sensing and actuation technologies that essentially is driving the smartness of smart cities. And that's something that we've been exploring for many different decades within our profession, whether it's traditional monitoring and control systems or cyber-physical systems. But really, smart cities goes one step further. And it's the two other layers that I think are the most interesting and the most important to highlight. And those would be essentially an understanding of the resource flows that layer on top of our infrastructure systems. That could be our energy. It can be resources like nutrients. It can also be things like finance. How does money flow into projects? And how is money used as an actuation element to drive smart city development? The other layer is the social layer, ranging from things like discrete choice of individuals within their society. How do individuals interact through social networks? And then finally, how do individuals react and essentially exist within the public realm? It's actually these two other layers that are the most critical aspects of smart cities and really push the limits of cyber-physical systems to go beyond just the physical to the social, so cyber-physical social systems. Now, if we think back to the 4 properties of resiliency that I introduced from the National Advisory Board on Infrastructure, those 4 R's being rapidity, resourcefulness, redundancy, and robustness, we see mappings of those layers being essentially inputs or associated with these 4 properties of resiliency. So we can begin to think about things like robustness and redundancy, which will often entail a lot of our physical parameters, but it also entails how we're essentially monitoring those systems, controlling those systems, financing those systems, and social responses. When you think about resourcefulness and rapidity, we're thinking more about the social and the resource flows that are necessary immediately after disasters or before disasters to drive resiliency within our smart cities. So at the University of Michigan, we're exploring opportunities in the smart city space through a number of different vehicles that are interrelated to one another. So within our department, we've been looking at smart cities and cyber-physical systems as a mainstay technology for civil engineering. And we've been modifying our curriculum and our research portfolio to essentially be one of the driving forces in this space. And we feel that this is very critical for the profession of civil engineering because we're beginning to see many other engineering disciplines coming in and start to define that space. But we are uniquely qualified because we're a profession about the common good. And we essentially want to leverage our experiences there to really drive development within the smart city space. So we're trying to do that through our education programs. We also established an institute that cuts across our entire campus called the Urban Collaboratory, which is a forward-looking or front-looking multidisciplinary research institute that works directly with cities. So we essentially use what's called a city as a client model where we go in, we talk to cities and city stakeholders to identify challenges and then map those back as research problems that our researchers at the University of Michigan can help us solve and implement sustainable long-term solutions for those stakeholders. The other center that we have is the Center for Smart Infrastructure Finance. The director is here today, Peter Adrians. And this is a sensor that's really looking fundamentally to answer the question, who's going to pay for all this, right? And I think that's a very important question that often gets overlooked, and I think it's really the distinct advantage that we have as civil engineers to answer that question. Because again, we're a profession that's not about essentially the personal wealth, but we're a profession about the commonwealth. And I think when we think about how these technologies are going to be deployed, we have to hold true to our tenets as civil engineers that we want to be in the service to society. So we're looking at how to answer that question through a number of different innovative approaches, including applying public-private partnerships through the adoption of fintech technologies. Looking at, for example, if we're deploying sensors, how do we monetize the data to develop new revenue streams that can go into our infrastructure, addressing infrastructure finance gaps that we see in much of the developed world. And we're also thinking about ways of tokenizing infrastructure services to actually increase their valuation, to essentially drive business opportunity within our profession. So the three of these elements at the University of Michigan work together to essentially work closely with city stakeholders, implementing a variety of solutions and thinking about how to finance that, fundamentally using technology that we're developing within our department. Now, in today's presentation, I'd like to highlight two brief vignettes of type of work that I do within this particular space. The first is looking at structural performance assessment, essentially applying cyber-physical system infrastructures to our highway networks. There we're looking to use cyber-physical systems to fundamentally understand what is loading our bridges. Often we look at bridges and we'll instrument our bridges, but we often do not have a direct measure of the load that's being imposed on our bridges. But we can use cyber-physical systems to answer that question or partially answer that question. We also want to provide data-to-decision frameworks that really drive decision-making by the asset manager, to essentially provide quantitative bases for doing risk assessments or resiliency assessment of the infrastructure. The other example that I'll highlight in today's presentation is the use of essentially looking at social systems within cities and trying to democratize smart city sensing for populations that essentially want to monitor and understand some of the challenges they see in their community. So let me begin with our first project. The first project is deploying a cyber-physical system on a 20-mile corridor that we've instrumented close to our university in southeast Michigan. So it's the I-275 corridor that goes from essentially the Ohio-Michigan border down by Toledo all the way up to the Detroit Metropolitan Airport. And we have 4 bridges along that particular corridor that carries highway traffic, as well as cameras and a weigh-in-motion station. And in today's presentation, I'll largely focus on 2 of those bridges that we've instrumented, the Telegraph Road Bridge that's been instrumented since 2011, and the Newburgh Road Bridge, which has been instrumented since 2016. The first bridge that we instrumented is the Telegraph Road Bridge, which is a very traditional type of bridge that we would see in the United States. Essentially, it's a steel girder with a concrete deck on top. But one of the unique structural characteristics of this structure is what's called a pin hanger connection, which is essentially a connection that moves the expansion joint away from the bearing and essentially is transferring the main span's loads off to wing spans that are supported in a cantilevered way by a pier structure shown here. This is a 40-year structure that has some deterioration that's quite common for a structure of that age and is being proactively addressed by the Michigan Department of Transportation. And you'll see, for example, distress on an abutment structure leading to some temporary shoring action of one of the steel girders, which has been subsequently fixed. We deployed in 2011 essentially a network of wireless sensors that we developed in my laboratory over the years called the Narada sensor node. And it collects over 70 channels of data. That's not because we need those 70 channels, but it is because it's a research project for us and we're looking at different ways of processing data. So we have different types of sensors on that structure that is looking at different response parameters, ranging from the vibration of the structure to its strain response. And for example, in our strain, we look at the strain profile under flexural response of the structure using strain gauges and what's called BDI bridge intelliducers that measure strain in the concrete of the deck. And we also have these pin hangers, which is one of the structural details of this bridge that's of primary concern to the owner. And we have a dense array of strain gauges on that particular hanger plate. Shown here is our deployed system. Again, we're using this Narada sensor node that we developed in 2005, but it maintains itself as a workhorse for the type of work I do in the field. This is just some evidence of how we essentially would deploy that particular system. It's more than just a wireless sensor. It includes the ability to use solar power to essentially collect power and recharge batteries like lead-acid batteries, which are necessary for the type of climates that we work in Michigan. We have things such as shut-off circuits that essentially allow us to be very power efficient, so we're not constantly powering our sensors. We only power them when we need it, as well as signal conditioning board and different types of sensing transducers, including accelerometers and strain gauges. The other bridge that we instrument is the Newburgh Road Bridge, which is just a few miles north of the Telegraph Road Bridge. Again, very similar history to this particular structure. It's nearly 40 years old. It's a few years younger than the Telegraph Road Bridge. It does not have pin and hanger connections. It's a very standard single-span bridge on structure. And we have a lighter array of 10 sensing channels on this particular structure that was deployed in 2016. In addition to our bridge monitoring systems, we have a weigh-in-motion station on that particular corridor that measures a number of parameters associated with the weightage of trucks that are going to be driving over those bridges. And we also have traffic cameras. And you can see an example of the Michigan Department of Transportation's traffic cameras. But we've deployed our own that essentially have an embedded GPU that will allow us to do analytics directly at the point of data collection. In this case, we're using a webcam that's going to monitor road traffic driving over our particular structures. And we'll embed detectors that allow us to detect real-time trucks as they're driving over our bridges and our weigh-in-motion station. Shown here are just some of the examples of the system deployed. Again, it's a solar-powered system, both our base station, which uses cellular communication to move data to the cloud, as well as our wireless sensor nodes, which are essentially using Zigbee protocols to move data to that base station, and then the corresponding camera system that's on the roadside of that particular structure. And we have a camera at all of our bridges, as well as the weigh-in-motion station. And we have one camera that's actually south of the system that's going to be a trigger to trigger our monitoring system. Once we collect that data, we'll push that data to the cloud. So we've been collaborating with Professor Kinshaw Lohr's group at Stanford, who does a lot of work in engineering informatics and data models associated with how we store data. So once we collect our data at our sensor networks and our traffic data from our cameras, we move it to a cloud database that essentially is a NoSQL type database, giving us flexibility in essentially the representation of that data within the database. So we're using Cassandra to essentially store that data, as well as to combine that data with information associated with the structure using bridge information models, which is essentially is a BIM type model that's specific to bridges and represents elements for bridges. Now, what we're interested in with the cyberphysical system is fundamentally is to link loads to the bridges. So what we're trying to do is we're trying to measure the response, or essentially the weight of trucks and cars that are in the corridor to the structural responses we're measuring at our bridges. So we have our Telegraph Road Bridge and our Newburgh Road Bridge. We're using detectors to detect trucks so that we can both trigger these systems but also to link loads. So we could look at correlation analyses of how does one structure respond relative to another based on the identical load profile that we can get by identification of the truck loads that are driving over our structures. The way we do that is we have one camera that's right at the entry point of the northbound segment of I-275 that's essentially always on and is real-time detecting traffic load to detect trucks. We're more interested in trucks because of the magnitude of load that they're introducing within our bridges. So we have an embedded detector that's embedded directly at the camera on a GPU that's at that camera to detect trucks. Once that truck is detected, that trigger essentially will trigger in the monitoring system, in this case the Telegraph Road Bridge, to essentially collect data roughly 100 seconds after that trigger, assuming that the truck is driving at a speed of 60 miles per hour. We give it some margin so that if that speed is slower or faster, we're still able to collect data from that particular truck. This is a very efficient use of precious resources like solar energy, particularly in winter months where we don't have long sun exposure. As we're trying to recharge these sensors, we don't want them necessarily collecting data associated with small cars or when there's no vehicles present. So this trigger strategy allows us to be super efficient with the energy we're collecting through solar power to collect data of primary interest, which is the response of these structures to truckloads specifically. Similarly, that trigger will also trigger the Newburgh Road Bridge about 120 seconds after trigger, again with some margin for error. And then about 360 seconds later, when that truck should be arriving at the WIM station, again, we trigger that system. That's going to give us bridge responses at these two bridges, a WIMS reading at the WIM station, and the associated video imagery that's going to allow us to identify those trucks. Now, to identify those trucks, we're going to use essentially a neural network strategy, which is one of the emerging approaches within the computer vision area. And we're using essentially what's called a single-stage convoluted neural network that essentially is going to allow us to execute at pretty high speed, giving us high performance with respect to the ability to identify objects within the field of view. And again, what we're trying to do is identify these trucks. So we're using one variant of a single-stage detector. In this case, we use YOLO by Redmond that was introduced many years ago. YOLO stands for you only look once, which essentially is a formed convoluted neural network architecture that's well proven to be a good detector of objects, depending on how you train it against different object class types. So we're essentially going to feed that imagery, push that through essentially a multi-layered convoluted neural network to extract out essentially bounding boxes that have some probabilistic measure of the detection of classes. And we're going to be training these convoluted neural networks against 3 class types: trucks, small trucks, and cars. And we want to be able to detect these in real time, particularly for our triggering action. So we're essentially using the version 3 of YOLO, YOLO v3, which was introduced by Redmond in 2018. And we use the full-fledged YOLO version 3 in an offline detection mode. So we're collecting imagery at all these different bridges and WIM stations. Those do not need to be processed in real time. So we use a regular YOLO detector for that. But we can use a light version which has fewer convoluted layers. Essentially, it has 13 convolutional layers in its backbone to essentially provide for real-time execution, trained in some precision and accuracy associated with that detector. So we're using transfer learning. So these particular architectures come pre-trained to a general class type, and we then train beyond that for the type of classes that we're looking at, which in our case includes essentially trucks, pickup, as well as cars. And you can see some of the training data that we collect. We use a combination of training data from the cameras that are at the roadside in our corridor, as well as online imagery to give us a little bit more richness in the training data set. We also hold back a quarter of the data for testing purposes that also has trucks, pickups, and cars to do a validation of this particular single-stage detector after training. And we're training against nearly 5,600 vehicles total between our I-275 data and online data. From a performance standpoint, we'll often look at the average precision of the detector, which essentially is looking at how well is it able to detect the object of interest, which in this case are vehicles. Also looking at essentially the mean average precision, which is averaging it over the 3 different truck class types. And we can look at different intersections over union from half, which is quite common in the computer vision area, to 0.75, which may be more desirable for our application here. And you can see some of our receiver operating type curves, our precision recall curves, showing the different performance features of the different detectors compared against other single-stage detectors like RetinaNet and single-stage detectors. Shown here is actually some of the results that we get for that system. So we'll capture a truck. That truck is essentially going to trigger the monitoring system up at the Telegraph Road Bridge, where we're synchronized in our imagery collection as well as in our bridge response. So you see the stream response there. Now that same truck comes up at our Newburgh Road Bridge. And then finally, we're going to see that truck up at the road station, where we're able to get a direct measure of the vehicle gross weight, the axles, as well as the distribution of weight on the different axles. Now, a challenge here is not just detecting trucks, but being able to what we call re-identify trucks, being able to say the truck we saw at one bridge is the same truck we saw at the next bridge. And that's called re-identification in the computer vision world. And we're using essentially a triplet network architecture to give us the ability to take imagery from the different points of data collection to identify that same truck as it's traversing through our cyberphysical system. And it's based on essentially a triplet loss function with a defined margin. And we're using the YOLO version 3 tiny implementation as the embedding network. So these 3 networks have the same weights, and they're being fed an anchor image, a positive, which is a secondary image of the same vehicle, and then a negative, a different vehicle. And we're training that through a backpropagation method to give us the ability to identify with high degrees of precision, essentially the same vehicle at the different locations in the network. Once we do that, what we fundamentally have at the end of the day is essentially bridge response data to the same truck load, as well as a direct quantitative measure of the actual load itself that's collected at the WIM station. And that provides tremendous opportunity for us now to correlate bridge behavior to a direct quantitative measure of the weightage of the truck. It may not be a measure of the actual dynamic load in the structure, but it's better than what we had before, where we would just typically deploy sensors and only get responses without direct measure of the truck load itself. Now, what we can use that data for are things looking like correlation analyses, looking at, for example, the peak bridge response against the measured vehicle weight. And you'll see here, depending on which lane that truck is, this is 5,000 truck instances that we've collected over a 1-year period with our cyberphysical system. And you'll see a fairly linear behavior, as we would expect for these type of structures, against the gross vehicle weight. There's large scatter here because we're just using a very crude measure of the weight. We don't include the weight distribution, nor it's essentially distribution weight on the different axles. But where we see essentially less scatter is if we look at the relationship between the peak response of one bridge against the peak response of another bridge. And we begin to see correlated analyses that may allow us to build relationships between bridge responses in the same network. And the reason we can do that is because each dot in the scatter network corresponds to the same truckload being observed at the different points of data collection within that particular network. Now, one of the things we're doing with the data is actually trying to aid the decision-making of the bridge manager or the asset manager. And the current approach to decision-making by bridge managers is fundamentally based on visual inspection. It's a time-tested approach that has a very, very good track record for managing our assets. So visual inspection includes a visual inspector that goes out and is looking at different bridge components and assigning a condition rating. In the United States, that's often on an FHWA scale of 1 to 9, 9 being a component's in excellent condition, a 1 being in very poor condition. Based on the condition rating assigned, these departments of transportation have very well-established decision-making processes that are triggered based on condition ratings. And that's very important, because what we're trying to do with our bridge monitoring systems is drive decisions. So we have to embed our monitoring system within that decision framework that exists, which today is based on condition ratings. Now, in the structural health monitoring field, we think about deploying sensors, analyzing that data in some form of an assessment, and then to try to use the output of our structural health monitoring algorithms essentially to do the same thing as visual inspections, which is manage structural safety at a defined cost, right? But the challenge is that this particular approach has not yet borne fruit in terms of being able to truly drive decisions, unless we're looking, for example, thresholding performance and looking for extrema that goes beyond a defined threshold. That has proven to be a successful approach to using monitoring data to make decisions. But we're talking about just everyday type decisions, these asset managers. So our approach is to use a reliability framework that allows us to essentially look at how is the structure performance relative to its limit state, quantifying that based on the structural monitoring data that we're collecting from our structural asset. And we'll use a reliability framework to do that, the same framework that is the bedrock of essentially our design codes. And based on that reliability assessment, we provide a quantitative approach to repair action. But we're doing so complementary to the visual inspection process, which is largely driven on the condition ratings. So the challenge for our research is to combine condition ratings to a reliability assessment. And if we can do that, we can essentially process our data, correlate it to condition ratings, and then use established existing decision-making processes that many of these DOTs already are using based on condition ratings. To do that, we're essentially looking at the performance of the structure largely in its elastic regime. So that's one of the challenges structural health monitoring algorithms have had, is that they largely think about damage as essentially introducing distinct changes outside of the elastic regime. And that's one of the reasons those methods have been very challenged in their ability to be applied to real structures like bridges. So here we're essentially looking, what is the performance of the structure with the structure existing for most of its lifetime in that elastic regime? And we can do that by looking at essentially the demand capacity, a very traditional approach in the reliability field, and trying to describe that in a probabilistic way through, for example, a scalar such as the reliability index or beta. So what we'll be doing is we're linking these betas that we can empirically derive from the monitoring data that we collect to the condition ratings. And we can think about condition ratings as essentially as increase in demand on the structure due to deterioration. And I'll show some examples of that from our Telegraph Road Bridge. The particular area that I want to focus on is those hanger plates. These are structural details that are no longer permitted to be used in the United States due to the Manassas Bridge failure in the early 1980s in Connecticut, where essentially there was rust and deterioration on the plate behind that essentially pushed that plate, it walked the plate off its pin, leading to a shearing on the corner of the pin and a brittle failure mechanism of that bridge, so they're not really used. Now, what are some of the challenges with these hanger plates is they corrode. They corrode on the bottom pin area, largely because they trap dirt and sand behind the plate, which when it's moist, essentially sits there and begins to corrode that steel plate. And you can see one of these hanger plates has been taken off of a different bridge in the state of Michigan, where more than half of that section has been corroded away. Now, this plate will continue to operate in its elastic regime, but it's seeing increasing demand because it's losing area as it's aging. And that's a classic example of what we mean by a component that's going to behave elastically, but we're trying to identify damage, in this case, the deterioration of its section. So we'll be using those strain gauges that we've installed on those hanger plates to do this in a very data-driven, quantitative manner. Shown here, for example, is a response from those different strain gauges on that hanger plate under truckloads. So this red box essentially corresponds to a truckload that we've collected. And what you'll see is that this particular plate is not behaving in the classical way it's interpreted from a design perspective, which is it's designed to act like a purely axial element. But it's actually not. And the reason why it's not is you'll see in-plane and out-of-plane bending being developed in that plate. And that has to do with friction and corrosion that's developing between the pin and the plate. It's locking it, leading to in-plane and out-of-plane moments that the designer is not accounting for within the design process, or at least not accounting for explicitly. And you can see, for example, differences in that in-plane strain that's associated with those moments in that particular plate from the data we collect. Now, what we'll be doing is we're trying to link the condition ratings that are well established, which is essentially the basis of our visual inspection methods in the United States. And you'll see here in the FHWA scale some clues that help us to actually begin to quantitatively link to empirical data we're collecting from monitoring systems. And the clues you see here are highlighted in red. And it's basically saying if a structure is in perfect condition, brand new, it gets a 9 rating. It has no deficiency. But if you start to see minor section loss, you go down to a 5. If you have 10% section loss, a direct quantitative measure deterioration, you go down to a 4. 25 section loss, you go to a 3, so on and so forth. This is the necessary clues that are required to establish now a direct linkage between a reliability index and our condition ratings. So the way we're going to do it is we're going to model these different, essentially lower limit states, if you will, from a reliability standpoint in a modeling framework to essentially establish what are the associated betas with each of these deteriorated conditions within our structural element. We'll be looking at 2 limit states in this particular example. The first is essentially yielding due to axial load in the net section, which is down by the pin, as well as looking at pin torsional yielding. These are 2 what we call measurable limit states, meaning we have data that can be used to actually input to many of the live load parameters that are associated with these limit states. So we develop essentially a finite element model that's going to take those different deteriorations that are associated with the different condition ratings, apply them to our model. So in this case, it will be section loss as well as friction along that pin hanger plate surface, and to perform a first order reliability method to establish beta. And that's what you see here is section loss versus interface friction. What is the associated beta for each of these conditions? Because in the case of section loss, I essentially have condition ratings I can now link to because of the established quantitative measure associated with some of those condition ratings. Once we have that, we can now, based on that relationship between these reliability indices, beta, and condition ratings, we can take data that's coming off of our structure. You'll see here are some histograms associated with strains. So in the case of the first limit state, we're interested in essentially yield, the dead load, live load that's axial to that plate. But we can measure parameters like the live load, which is essentially strain gauge 4 down at that net section. How about that area? How are we going to measure the area? Because again, it's section loss that we're losing there. Well, if we look at what the net stress is against the gross section stress, we see that that's relatable to both the gross area up at the midsection versus what is the area at the net section. And we can see that relationship is actually measured in the ratio between the strain we measure at the center of the plate to the strain we measure down at the first pin. And that provides the ability now to use these 2 strain gauges to feed this limit state function to extract out that reliability index and then map that to our condition rating. So you'll see here from the actual structure, one of the hanger plates, we have very high reliability indices indicating condition rating of 9, even though the bridge inspector is actually rating that as a 7. So that's a very exciting approach to now taking structural monitoring data and moving it toward an established reliability framework, which again is understood by the structural owner because most of them come from the design realm to start making decisions based on condition. So the last area that I want to highlight very quickly is an adaptation of some of these sensing technologies to monitor social systems within cities. There's a lot of interest in urban sensor networks in the smart city realm for a number of different reasons. It allows us to provide data that's associated with the different urban processes we see within our built environment, whether they're processes that are physical, social, what have you. But today, if we look at urban sensing, these are approaches that are largely reliant on essentially the government sector in collaboration with the private sector coming in, selecting the sensors, deciding what to sense and where to sense it, and putting it out, without a lot of good interaction with critical stakeholders like community members within these cities. And that's going to challenge nodes of governance within our cities because it's creating an asymmetry in the information that's available to different stakeholders. So the politicians, the political domain can take advantage of these sensors to essentially provide, for example, better services that ultimately may lead to essentially their ability to stay in power. But community members often are not the direct beneficiaries of many of these urban sensor deployments that are being deployed. And that's a real challenge for the widespread acceptance of urban sensing within urban environments. Now, we have a project that we call Sensors in a Shoebox, which is really looking at trying to deploy sensors not to the government sector, but essentially to communities, allowing communities to take these sensor platforms and deploy them themselves to collect data that they want to collect data about, right? Things that they're interested in studying. So we have a very simple to use sensor network system that basically you essentially give it to a community member, they turn it on. It has a number of different modalities that can be plugged into it, and then community members can collect that data. It uses solar power, so we don't have to tie into dedicated power systems like you do in most urban sensor networks. And it also uses cellular communication so that we don't have to tie into things like fiber optic networks within cities, providing community members full power with their data collection capabilities. That's essentially pushed to the cloud where data is essentially visualized for community members to use and interpret. And we have a number of different ways of providing that data, from portals to things like Twitter. We use, for example, Twitter to just tweet data right off of these sensors, giving the public the ability just to subscribe to a Twitter feed associated with a sensor. And that can be one way to use data beyond very cumbersome or difficult to use for some community members, data portals that we may put online. Now, essentially, we're deploying these systems using a network platform that we call OurBar. This is an open source platform that we've opened that essentially is open source both hardware and software for essentially these urban sensing applications. And it uses a very low power microprocessor. We have GPS capabilities for applications that are associated with tracking things in cities, as well as cellular modems. But these modems can be swapped out for things like LoRa modems or other types of telemetry methods that we may see emerge in the smart city space. Showing here is just a picture of that Urbano, and you can see, for example, the cellular modem that we embed on it. It's on a door-to-board configuration, so we can pop that off and put in, for example, different types of radios depending on the application. More recently, we've been deploying a lot of LoRa networks in Detroit based on this platform without cellular to save cost. We can connect data like air quality data or pedestrian counters through passive IR type sensors. And this is an example of it. This is actually deployed in a deployment up in Grand Rapids where the city was interested in pricing the permitting of food trucks. Today, that city essentially prices food trucks just based on per use, one truck, one cost. But the city is interested in looking at how much business is the food truck doing based on measures of actually customers coming to the food truck to start pricing food trucks differently based on location in the city, right? Trying to monetize that curb space more efficiently. So that was one application we do for Urbano. The other applications we've looked at have largely been air quality applications using low-cost air quality sensors looking at NO2 and SO2 pollutants, as well as ozone within urban environments. Once we have that platform, we use a commercial cloud-based environment to actually move data to the cloud and to use established visualization tools. We use a platform called Exosite One platform, which is relatively open for the user community to use. And one of the advantages of moving data through that particular platform is that we have a variety of different ways of dispatching that information. And again, we do a lot of posting on websites as well as Twitter feeds of our data. And you'll see an example of some of the feeds that we pull off that portal. Now, we've been deploying these sensor networks in Detroit, which is roughly about a half hour from our campus at the University of Michigan. And Detroit is what we would call a shrinking city in the United States. Again, as I said at the outset of the presentation, it's seen 60% population decline over 60 years. And that had to do with a tectonic shift in the automotive sector, right? Detroit being the motor city was historically relying on manufacturing jobs. And in fact, there was mass waves of migration within the United States through the 1940s and 50s that moved populations from the South up to Detroit to essentially work in those factories. But as those factories disappeared starting in the late 70s all the way up to modern day, we saw a dramatic population decline. And this is an area of Detroit that at one time would have been a very prosperous, very populated neighborhood that today is largely unpopulated. And so much so that the city has gone in and eradicated most of the vacant housing that's there. So you'll see large swaths of urban space in Detroit that essentially have one house and entire city blocks that are completely empty. And that's one of the challenges, but it's also a symptom of essentially the encoded poverty that we see in that city. So large segments of that city have incomes on a per capita level of $10,000 or less, which is incredibly far below the poverty line, meaning it's very difficult for that particular community to have social mobility within those spaces. Now, we've been working largely with adolescents in the city of Detroit because adolescence is really the age group you want to target if you're trying to keep individuals in a city as they essentially are trying to socially mobilize. So we've been working largely with middle school and high school students through a variety of different partners in the city of Detroit, including some charter schools and some outreach organizations like the Detroit Hispanic Development Corporation, implement our Sensor in a Shoebox program. And essentially, that particular program selects a select number of students. So you'll see some of my PhD students shown here, working directly with the students that we have in our cohort. And we ask the students to first identify things that they're concerned about as community members within their community. And you can see a list of some of the problems that they've identified through some of our working sessions. And one of them there, like pollution, that's something that we can measure. That's something we can actually collect data on. But we teach the students three forms of data collection. Field observation, go out, visually look at some of the problems, quantify the problem based on visual observation. The other are survey methods. Start to talk to other members in your community, talk to some of the leaders of your community and get their perspective, and then collect data using our Sensors in a Shoebox platform. Now, the two things we've looked at with two different cohorts have been essentially green space. There's a push as the city revitalizes to make it what's called a walkable city. So the city planner, Maurice Cox, who previously redeveloped New Orleans after Katrina, is now the city developer or the city planner for Detroit, is trying to implement solutions, urban planning solutions that are based on walkability of the city to strengthen community ties within the community. So there we see a city that has tremendous park access, but is largely under-resourcing investments in the park. So the city is fundamentally no longer curating those parks, no matter how critical they are to prosperity of these neighborhoods. Also air quality, particularly Southwest Detroit, has 2 coal-fired power plants and also has a large number of steel and aluminum mills that essentially introduce a lot of pollutants. And in fact, it's an area that the EPA is monitoring with a dense network of air quality sensors themselves. But the problem is we see historically high levels of asthma among that youth that live in those areas due to those pollutants. And that's why these are 2 areas of interest that these students have identified. Shown here is one area that we've used in the city. It's essentially one of the greatest assets of the city of Detroit, which is its waterfront. So this is the United States, and to the south of the United States is Canada, essentially Windsor, Ontario, is to the south. And essentially this waterfront is a large park that before in the early 2000s essentially was fallow land. You'll see here underdeveloped land, but if you look after 2003, massive investments, hundreds of millions of dollars of redevelopment money has gone in from foundations, industry. So this is the Ren Center, General Motors headquarters. They've contributed a significant amount to make it look like that today. So it's a beautiful asset of the city of Detroit. The challenge though with this asset is the community members find it difficult to gain access due to Jefferson Boulevard, which cuts that park space off. To address that issue, there's a number of cuts that have now converted old rail lines that service essentially an old, essentially port on the Port of Detroit. They've converted these old rail lines now into walkways. One of them is called the Deskinder Cut. So it's a rail-to-trail initiative in the city. This is what it looked like before. This is what it is today. It's a beautiful, beautiful part of downtown Detroit, coming off the riverfront up to an area called Eastern Market, shown here. But there's two more cuts, the Capano cut as well as the Beltline cuts that is about to begin redevelopment. And we've been working with the Riverfront Conservatory to essentially do pedestrian monitoring with our students. So the students that we've embedded develop these platforms that essentially use passive IR to look at the number of pedestrians that are coming across these cuts, to begin to provide quantitative empirical data to the park owner to essentially curate these spaces to draw community to the waterfront. And that's very powerful, both for the students that are deploying these sensors to see the usage of these public spaces, but also for the owners of those spaces to curate them better. For example, some of the things we've learned, we could look at cumulative pedestrian counts of those spaces and understand limitations in that space. For example, we see high use around public areas, but an area that deploys sensor 4 doesn't even trigger. Why is that? It's largely due to, for example, obstructions in that pedestrian pathway due to water. So poor drainage condition and broken stormwater systems making these pedestrian paths unpassable. So we don't even see the pedestrians. And that's something we teased out with the data we collected. And you can actually see our sensor in the Shoebox deployed there. We also look at things like air quality. So for example, how does air quality correlate to use of these public spaces? So that's another area of concern of these students because of the high rate of asthma many of these students in Southwest Detroit see. And this is just some measures looking at nitrogen oxide, sulfur oxide, and ozone, the three major air pollutants, including particulate matter, that essentially can trigger asthmatic conditions or can challenge oxygen uptake when you have high concentrations of ozone in the air. And what's interesting is that these peak measures of air pollutants peak at the peak times when the park is in greater use. And that's one of the potential uses of the data is to inform individuals of air quality indicators before their peak use. So just some parting remarks. We've seen a continual evolution in the smart space, beginning with smart monitoring, smart control. Today we're seeing a lot of work in the cyber-physical domain, but that's really maturing into a more exciting space that includes social and resource flows, essentially the smart city space. I highlighted two applications in this talk. One was data-driven decision-making for assets based on monitoring data. It's a primary concern for most cities that are dealing with how to manage their infrastructure with smaller and smaller resources to apply there. And that's one of the reasons we're also looking at financing mechanisms through our Center for Smart Infrastructure Finance to address that. And some of our ongoing work is we continue to work with Detroit in our urban sensor network deployment. We have now about 30 sensors deployed in the city, and we're trying to increase that number through our programs with our students. We've been looking more continuing discrete system modeling of the social dynamics. We also apply a lot of computer vision methods there. So Detroit has a pretty extensive security network camera in many of its park spaces that we're using to essentially identify park usage through computer vision methods using the same tools I use to identify trucks. And we're also working with Peter Adrians, who's here today, private financing models for infrastructure investment based on performance-based financial vehicles like performance-based municipal bonds. If you're going to have performance-based municipal bonds, you have to be able to quantify the performance. So we're looking currently at linking a lot of our health monitoring data to actually driving a lot of those particular metrics. So with that, I'd like to say thank you to the organizers of the conference for the invitation to give a keynote this morning. Thank you very much.